All right, so normally I will just start a page with maybe some announcement reminders. We don't have many things to say today, so I'll just mention to you verbally quickly. So if you go to the lecture site, which I talk about from the syllabus section, and by the way, so you can see the lecture recording from the very first class about course syllabus. I can see some new faces today, right? Maybe you didn't attend the first class, so please just make sure you catch up with the material from the first class. Nothing technical, just about the course policy. Just make sure you're familiar with them. And then, especially for the syllabus. As I said, if there's anything that might change within the coming 1 week or two, I'll definitely let you know explicitly. Otherwise, you can assume. We're going to run the course as we talk about on Tuesday. And you can see the slides I'm going to talk about today is already there. And one thing I just want to draw your attention to, which I also kind of sent you guys some reminder in e-class today. You can see that for today, there are 2 documents over here. And the left-hand side is going to be the annotated page I'm going to publicize after today. There's another one here on the right-hand side. So that's the blank pages I'm going to use on my iPad to annotate different notes. So for those of you who may want to print them out, or maybe load it on your tablets, feel free, right? It's just a learning resources for you. Okay, I'll try to do that consistently for every class. May not remind you, it might be a little bit bothering you, every time if I made the notes available. Check it maybe about 1 or 2 hours before the class. It should be there, okay? Just always check, okay? All right, apart from that, I don't think there's anything else I should really say. Guys, any question about the course? Any confusion about syllabus? Yeah, go ahead. Sorry?
Was the iClicker given?
The iClicker, not yet. I'm going to do that. So we're going to do some trial attendance for iClicker a little bit later today, right? Just trial. So it's only for you to get familiar with the process, and then from next Tuesday, we'll do the real thing. I may not take attendance for every class, but just take it randomly. Okay. All right, so let's now move on. So today is still just mainly going to be about introduction. So I'll talk about the different stages for compilation, and then I'll mention certain terms that might sound familiar to you from 2001, Theory of Computation. I'm pretty sure all of you have taken that as a CS major. There will be some interesting challenge which will address the limitation of what a compiler is, which it might be also worth talking about it in the introduction. And then I'm also going to give you some example compilers, maybe ranging from the more typical use or conventional use of compiler, and the kind of compiler which we're going to go towards for your projects. And also for this year, I'm also going to summarize about 2 previous projects that we did in 4302. And for this year, you're going to get a brand new project. But I think you're going to get some idea. I think it'd be worthwhile mentioning about the project that you can actually think about. And feel free to really create your side projects, as you go along with the course. So once you learn about the Antler 4 tutorial videos, which I'll assign to you around the reading week or study week, is really open up unlimited number of opportunities for you to build a compiler. All right, so today, still introduction. Okay, just to clarify the general terms, and then next Tuesday we'll start talking about scanner, which will be whose theoretical foundations about DFA, NFA, regular expression. That's something we're going to go through. Okay. All right, let's now go back to the slides. So last time, the only thing technical that we spoke about is about semantic domain, right? Let me just recap very quickly, just for that one. So if you review the notes, semantic domain is really to define, each semantic domain is really trying to define some specific meaning. In order for you to define the meaning, you have to know what's the vocabulary. So we gave you 3 possible semantic domains. Of course, there are unlimited number of semantic domains. Number 1 will be object orientation, what you learned from 1022, 2030, and 2101. Classes, objects, aliasing, anything that can help you define the idea about object orientation, it should be the vocabulary for that particular semantic domain. And for database, for example, entities, tables, primary key, foreign keys, etc. That will define relational database. And also predicate logic, what you learned in 1019 and 1090, right? And what I mentioned also about object relational bridge. So there's a very practical usefulness for switching between Java and also SQL database. You can think about Java-like language is actually very good for you to specify big projects with hundreds of classes interacting with each other. And then somehow for efficient and mass storage of these classes or objects, you can turn them somehow into SQL database. So for those of you actually who took the database course before, you know that the primary use for SQL database is really for mass storage and efficient queries. Yeah?
Could you apply that to the other domains? So for example, say object predicate bridge, and make a bridge between any of them?
Yeah, it's a very good question. So let me just repeat your fellow student question. Basically, she was asking whether or not, let's say, what I talk about is to build a bridge between SD1 to SD2. Yes, in theory, you can also try to build from SD1 to SD3. However, I can mention that right away. That's actually somewhere in the slides. Some people like to think about compiler is really about turning something into something else. Very general and very vague, okay? Let's think about the very idea about compiler. Think about a compiler is more like a transformer. Transform one thing into another form. Or translator. And if you think about translator, for example, if you want to translate from English into Chinese, or you want to translate from English into French, that will involve translating from meaning into one language and preserve that in another language, right? So that's also translator. So you can think about compilers really to take one form into another while preserving the meaning. So let me just write it down. Transformer is really about going from one syntax into another. One syntax into another syntax. And if you think about compiler as a translator, it's really try to preserve the meaning. Even though we are changing from one syntax to another, it's only a structure, right? It's very superficial, but the underlying meaning should be the same, preserving the meaning. Okay.
Is there like a blank template for the notes? Or
Is there
a blank template for the notes?
what template, sorry?
A blank,
A blank template.
yeah.
What do you mean a blank template?
Like you have an empty sheet over there.
Okay, I'm not exactly sure. Maybe you can take that a little bit later. Okay. All right, so we got transformer, translator. Okay. So for your question specifically, if I am given, let's say, OO, Java-like language, can I somehow compile that into just predicates logic? This is actually a very open-ended question. The correct answer should be, number one, do you have some well-defined syntax for this input? So the question you want to ask yourself is as follows. Question number one. Is the syntax or context-free grammar, right? You learned about it, context-free grammar. You actually define how should we structure, like how the structure turns together. Define. More specifically, if you talk about Java-like language, do you only want to support classes, attributes only, or you also want to support extends keyword for inheritance, polymorphism? So you got to decide, right? So do you want to support the full features for OO, or do you want to support a subset? Do you want to support the entire set of, I would say, basic and advanced OO features, or just a subset? If you say you want to support everything in here, then it might be more challenging for you to see if you got the corresponding concept in the logic, right? You always have to see whatever you want to translate from here into here, is there any corresponding concept? So that's the second question you want to ask. Okay, so second question. The second question is actually more critical. Question number two. Question number two is every concept in the input corresponding to some equivalence in the output. Let's say you want to support, let's say, polymorphism. In that way, if you find that in your particular logical language, you don't really have a way to represent polymorphism. In that way, the compiler would not be feasible. If you think that's possible, yes, it would be feasible. So I think question 2 is absolutely critical. Okay, so this is really the critical question. Okay. All right. Okay, it's a very good question, but I just want to address maybe up to now. So I think as we go a little bit more, I think we can discuss more. But of course, the project which I'm going to give to you after the reading week, it will be a feasible one. So from the input to the output, it should be possible. It should be possible to find the corresponding parts. Right? But in general, you don't necessarily just be able to convert from one thing into another, always. Okay? But at a vague level, you can think about compiler is really trying to transform one thing into another. Okay? All right? All right, let's now move on a little bit. And I'm going to go over that diagram a bit, but we talk about semantic domain. Okay. Okay, that's something we just covered. So let's now go over this diagram. Okay, quickly. So this is the most general form of a compiler. Of course, inside the compiler, there might be different stages, which we'll dive into a little bit later. For example, inside the compiler, we're going to divide into scanning, parsing, and also semantic analysis, 3 different stages. But for now, let's just say compiler is a big component. It's a software system, or like a Java project you're going to submit for your final projects. Okay? Let's talk about what's going to be the input for the compiler, and what's the output that's going to be produced by the compiler. Let's talk about that level first. Okay? So there will be some input program you have to take. Input program. Let's just say one example, just make it a little bit easier for you to understand. Let's say the example compiler we're talking about is the object relational bridge, let's say. Object relational bridge. Okay, let's say that's the example compiler we're talking about right here. Okay? So the input is just going to be something.java, like a Java file, let's say a single class. So the input over here is just going to be, let's say, my class.java. It's a specific input. Okay? We can think about this as like an input instance. One instance of the input. At a concrete level, I actually want to convert my class.java into some SQL database queries. That's kind of equivalent. Okay? I will show you guys, maybe not today, but maybe on next Tuesday, I do have some example compiler which will convert Java-like language into SQL, so that, to give you some idea. But for now, let's understand just at a conceptual level. What about the output? So for the output here is just going to be, let's say, SQL database. Okay? And you can think about a SQL database, let's say my db.sql. Right? You can think about it might contain 2 parts in the database, right? You may have some table declarations, and also you got the queries. But these are the 2 parts. So somehow, in your myClass.java, okay, I can say a little bit more. So in myClass.java, you actually got things like classes, you actually got attributes, and also you got methods. So these are the vocabulary for this particular semantic domain. We are going to translate that into another semantic domain. But somehow the requirement is the tables and queries should accurately reflect the meaning of the classes, attribute, and methods. Somehow. That's the requirements. Okay? So compiler over here should preserve the meaning of the input OO program in the output relational database program. Even though this and this have different syntax, they got different structure, but their semantics should be the same. Okay, I'll show you some concrete example on Tuesday, I promise. Okay, just maybe not have enough time for today. Okay, so this is just one example compilation. Think about what we're talking about over here. It's just one example run of the compiler. So this is a single run of the compiler on specific instances, on specific input and output. What's really important for you to think about is the input program can be arbitrary. It can be some arbitrary Java code. You just imagine if you actually compile you try to write some Java program in Eclipse, whatever you write, whatever your fellow student write, they can always be compiled and run. Right? So the Eclipse compiler should be general enough to take any arbitrary Java program. So that's why here is what you guys will have to implement in your project. Well, that's something you're going to learn. Most important thing from this course, which I'm going to highlight here, this part here. All right, so what I highlight in pink, yeah?
What is the yellow text thing?
Sorry?
What is the yellow text thing at the bottom? Right?
Which one? This one here?
Yeah, yellow text at the bottom. Right?
This one?
Orange. Yes, orange. Yeah.
A single run of the compiler on specific input-output. Okay, and here we'll talk about we want to somehow generalize the input program into some grammar you will conform into. Because once you're given the context-free grammar, you can generate an infinite number of possible strings from that particular grammar. So once you're given the grammar for the Java language, you can generate all possible valid Java programs that can be compilable into the corresponding C code. Okay, so I'll just say over here. So this one here could be the context-free grammar for Java. This one defines all valid Java programs, which can be taken as input to the compiler. Okay? And similarly, if you look at the output here, for the output language, right here, it should be also the grammar, but for another language. So this will be, for example, the context-free grammar for the C language, which defines all the valid C programs. And of course, the syntax over here is about how you can define the table, how you can declare the keys, and also how you can define the queries. Okay. And the compiler, let me say one more thing. The compiler here, the actual implementation. Okay, I'll put a star here. Okay, I'll put here. The implementation of the compiler will work or define is defined at the context-free grammar level, and i.e. is going to be abstract syntax tree. So I'll just mention the terms right now because that's something we will need to see a little bit later. Okay, so abstract syntax tree. You'll see some example about abstract syntax tree in just one moment. Okay, so this part here is also very important. The way you define how the compiler works is you have to work at a more general level. You cannot simply say, given this particular input, I'm going to generate this particular output. Not really. You want to say, taking some arbitrary input program as defined in some CFG. I'm going to program the corresponding methods which will turn that particular grammar into this particular grammar. That's basically what you got to do. Okay? And in the Antler 4 tutorial you're going to study later, I also show you the minimum example, like how you can do it. Might sound a little bit abstract at the moment, but that's okay. We're just doing the introduction. Okay? Let me recap very quickly, right? So this is kind of the simplest workflow you can think about what a compiler is. Compiler itself is a component which has many internal parts, which we'll elaborate just one moment. And from the compiler, you have some input, you have some output. The input must be well defined with respect to some context-free grammar. Similarly, the output should also be well defined with respect to some output like a context-free grammar. And then whenever you want to define the transformation between the input and output, you have to work in terms of the grammar. Okay? So that's the critical parts. All right? Guys, any question? Okay, good. Well, we'll dive into more details as we go, right? For now, it will be enough detail, okay? Context-free grammar number 1 and context-free grammar. You can think about context-free grammar number 1, and also this will be context-free grammar number 2, right? You got one grammar and you got another grammar. Okay, so there's a syntax you have to learn how to specify grammar, which you learned in 2001 anyway. Okay, we're gonna review that too. All right, so semantic domain, and okay, so we're done with this diagram here. Let's now move on. And this is exactly what your fellow student just pointed out, right? If we want to turn one thing into another, is it always possible? Not necessarily. There's got to be some limitation, okay? So these are the important two things I just mentioned. You got to make sure the syntax is specifiable as context-free grammar, both the input and the output. And also the meaning should be also programmable, right? So something we'll see. All right, so let's do some mental challenge over here, all right? So this is what I normally refer to as an A+ challenge, okay? I'm going to present to you guys a challenge over here. Any one of you can somehow implement this challenge, the solution, as a compiler, and you don't need to take this course anymore. I'll give you an A+ immediately. No question asked if you can do it. Excited? Okay, good. Let's see. Here is the program I want you to implement, okay? You can implement the program in either Java, Python, C#, C, whatever language you like. Doesn't need to be Java. Here's the program. Recall back in 2030, you learned about the idea about dynamic type for variable, right? Okay, so let's say your compiler is actually going to take two inputs. It's going to take some Java file, something like this. So Java file can be my class, and then you have some main method. You declare, oh, let's make some assumption here. So let's say we have one class somewhere called students. And we have another class called resident students. And RS extends from students, so it's a subclass, let's say, okay? And then I declare S to be of type students. Let's say somewhere in the last line, I say S should be a new object of type resident students. After this particular line, I know that the very last dynamic type for S should be resident students, right? So now just imagine we don't have anything in between. We only got this line here and this line here. So if I only got these two lines, so now give this program to your compiler and ask about what's the last dynamic type for S. The output from your compiler should be resident students, okay? Now the question is, are you able to implement a compiler that is able to take some arbitrary Java program, something like this, and then always tell me the last dynamic type of S? That's the question. If you can do this, you get an A+. Any one of you think you might be able to do this? Or any insight would like to share? This can be linked back to something you guys learned about. Maybe you don't really realize it has some practical value back in 2001. Okay? So it turns out this challenge here, oh, sorry, go ahead, please.
So I guess we're not able to run the program first. We just have to look by the...
You don't run the program. You also talk about some critical insight, but let's not get there just yet. So, yeah, you don't really run the program. You're given the text of the program and given the variable name. Your compiler is somehow going to process these two inputs whatever way you like, and then tell me what the last dynamic type is.
Could we just look for the new keyword and then the latest line that's on and see what class that's?
Okay, the question, yeah, okay, very good insight. If I don't have anything in the middle, yes. If I don't have, or specifically, if I don't have any loops, I can simply go to the last line with a new keyword, yes, and then see what it is. But it's only for that particular scenario. But what if I have some complicated loop? What if? Okay, I'm just trying to present, in some way I'm doing some informal proof about why this is infeasible. Okay, for here, what if I have some while loop? And the while loop actually got some arbitrary Boolean condition over here. Okay, you can think about it is arbitrarily complicated. Arbitrarily complicated condition. In that way, how can your compiler analyze even if this loop or even terminates without running it? Right? That's really the insight. Okay, let me say a conclusion, guys. I don't want you to, we don't want to dive too much into this. It turns out this is not just an A+ challenge, because if you can implement such a compiler, what you deserve is not an A+. You deserve a Nobel Prize. Okay? Because this is an undecidable problem. Have you heard about undecidability back in 2001? Maybe heard about the term, right? Okay, so this is actually a typical undecidable problem. We wouldn't go into the actual proof. Let's not bother. I want to give you the insight once more. Here's the insight. If your compiler is going to somehow analyze the input program over here line by line, if you hit anything like this, like a while loop, and you have some complicated Boolean condition, you don't even know if the loop is going to terminate so you can get to the last line. You don't even know. What's the best thing you can do for your compiler?
Assume the worst case scenario.
What's the worst case scenario?
So, say the compiler knows all the subtypes of a student. In this case, resident student.
Here, okay. So when you talk about worst case scenario, right? The worst case scenario might be this loop simply doesn't terminate. In which case, the last dynamic type will be undefined. However, you don't know if that will terminate or not. You don't even know, right? That's the really bottleneck. Yeah.
Okay, fair. But assuming that the program will run, it will end. There is no infinite loop. You could assume that it will use the most.
The last dynamic type.
The last dynamic type.
But the problem is, so you gotta make sure your compiler can handle arbitrary program. If somehow the loop will terminate, you gotta tell me what it is, the last dynamic type. If it does not terminate, you also need to tell me it's undefined. But here is the problem. Okay, out here a little bit more. Okay, go ahead.
Oh, I was gonna say, I don't know if it's, well, like you said, I don't think it's possible, but I think what compilers do, they have like dynamic linking at runtime.
They have to somehow to simulate the program. That's the best thing the compiler can do. So somehow your compiler can do the following. Okay, here's really comes the insight, and then I'll just go a little bit, and then we should be good. The best your compiler can do. How about this part here? So this part here, I want to know whether or not the body of the while loop can eventually make the Boolean condition here false, so I can exit from the loop. Okay, so the best way for the compiler to know. The best way for the compiler to know if the body of the loop, terminates is by simulating it. When I say simulating it, it's just to really try to execute it somehow line by line. Okay? And simulating, sometimes people also say, try to interpret the body. Interpreting. And I'll put a star here. I'm just running out of space. When you try to simulate, here's comes the problem. If the loop itself does not terminate, does not halt, your compiler also does not halt. That means your compiler will never give a result back to the user. That's unacceptable. Okay? if the loop does not halt, oh, sorry. Your compiler also does not halt because you're simulating it. Okay, that's unacceptable. Because there's always such a possibility that your compiler may not halt, so there's no such a compiler, right, to really figure out the compile time, figure out the last dynamic type. And this actually also related to any programming IDE you're doing. Okay, let me just say one more thing, okay, if you don't mind. Okay, let me just give you the exact syntax. Let's say I have something here, students. And then let's say resident students. Or just RS for resident students, okay? And if I have students over here, S, which is assigned to new resident students. And let's say the following. Let's say in the resident student, we have some new method that's only available to resident students, let's say, okay? Let's say that one is to say double, let's say get premium rate, let's say. Let's make the assumption that this method here is only applicable to resident students. It does not exist in the students. Only exists in the resident student class. So here comes the limitation. So if you try to visualize this line over here, so we basically got S pointing to an object of type resident students dynamically. So the actual dynamic type for S is really resident student. However, if you try S dot get premium rate, guys, it's a basic Java question, right? If you try to say S dot get premium rates, is it going to compile or not? Basic Java. Okay, I'm going to tell you it's not going to compile. Because somehow, when you look at S over here, it was only declared to be students. And the student class does not define the premium rate, so it will not compile. But you might be thinking that, why is the compiler so silly? Because after this particular line, dynamic type for S should be resident students, which should have get premium rate available. But the compiler is not able to figure out the dynamic type. This is like a very deep question you might be wondering, right, about the limitation for Eclipse compiler or any compiler. So whenever you get back to the programming compiler, like programming IDE, like an Eclipse, IntelliJ, Visual Studio, whatever, anything that's to do with inferring the dynamic behavior of a program is an undecidable limitation for compiler. No compiler can do it. All right? All right, let me write down the conclusion, and then that'll be it. It's kind of for the like a broad knowledge about what the limitation for the compiler is. A compiler's limitation is to infer the dynamic behavior of a program. Because the best way the compiler can really infer the behavior is by simulating it, which may never halt. Right? That's like a short answer, short justification to that. Right, guys? I know this one is a bit abstract, but I have to mention that, right? It's a natural limitation for compiler. So when you later on do the projects, you don't really want to try to really simulate the input program, because in theory you might run into non-termination, okay, whenever you got loops. Okay. All right, so that one you can think about it. I think since you guys are in the 4th year, you deserve some deeper knowledge about the compiler. That's why I want to really mention that.
So
At the top, what do you mean? Over here? So you may want to go back to the basic Java and think about these two lines, right? If you try these two lines, it's not going to compile. You're going to get a compilation error. Even though, at this point, the dynamic type for S is really resident students, but compiler cannot really tell. Because in theory, compiler is limited to not able to actually figure out the dynamic behavior for the program. Yeah, question, go ahead.
The other way around would compile, right? If we had resident student RS is equal to a new student.
Okay, that's another issue, right? So the other way also wouldn't compile, but for a different reason. Okay, so okay, I'll just mention that since you mentioned. Okay, so what your fellow student was saying is a different issue. So if you say resident students RS equals new students. By the way, this one also will not compile because in order for that to compile, this must be a subclass of that. But the problem is student is not a subclass of RS. If you feel a little bit hesitant about this, don't worry, because some part of this course is about to talk about some design pattern called composite visitor. You will need to know about this kind of thing. Let me delay that discussion for a little bit later. But it's okay. If you guys haven't really reviewed the idea about 2030, polymorphism, dynamic binding, it's okay. We're going to review it. Just make sure you got it before the exam. How about that? Okay. Okay. These are fun stuff. I think you definitely want to kind of know. All right. All right, so that's about this kind of A+ challenge. Don't try to implement it. It's not going to succeed, but just at least know there's a limitation there. All right, so this course actually is very nice to synthesize many good ideas you learned from the previous course in your CS degree. Let's just list a few of them, and then I'm going to dive some of them into detail just to give you some perspective when you do the projects. Modularity, right? It's about dividing your software into different classes, modularity, right? So what you really want to avoid is something called Superman class. Superman, okay? Superman class means you have a single very giant class which try to do everything. A giant class or module trying to, or responsible for doing everything. Responsible for doing too many things. This is something you would like to avoid. And the beauty about using an object-oriented language like Java is you can split the Superman class into different classes that's kind of interacting with each other. That's modularity. So what you really want is to apply the modularity principle right here. Modularity. And then conceptually, you got to divide them into maybe one class over here, and then one class over here. I'll just draw three, just for example. And you got another class over here, and somehow you may have different attribute declaration that's going to refer to different classes, right? They have some connection. So rather than having a single Superman class doing too much, you can divide the labor into different classes for separation of concern. Separation of concerns. So one simple way to tell if you really got modularity for your projects is I will look at maybe how many classes you have. Do you have a particular class that's way too large? Okay, that's a very superficial way to actually tell, at least. Okay? Of course, in your final project report, we would like to see how you will justify your compiler implementation actually satisfy the modularity criteria. It is important. Okay? All right, so that's the first principle, and let's now move on. Information hiding. I'll dive a little bit more into this, but information hiding simply means there are certain part of the attributes you want to make them as private, and some attributes should be as public. And only the public one and the public attributes should remain very stable. They should not be changed over the time. But for the private one, you can change as much as you like. Okay? I'll visualize this for you right here. Information hiding. So these are all very good principles you would like to apply in a practical way. So we may not be able to talk about each one of them in detail in this course, but since I mentioned the turn to you, you can feel free to maybe explore a little bit on your own how each principle can be put into practice, right? I'll just mention a conceptual idea for you. Information hiding means the following. If I have a single module, let's say I take one single module from modularity, right? Single module. Let's say this is my single module or the class. Conceptually, you can think about I can divide this class or module here into two parts, one public, the other one private. Okay? Let me use green to signal to represent any part that's public. So this will be the public. And the public part can be attributes and can be methods, right? Also, I got some the other part is private. Okay. And this part here will be the private part. Right? In principle, you can divide each of your module or classes into two parts, public and private. Let's see how the information hiding can be understood. If I got any external user who wants to use my class over here, they would know everything about the public because I made public to them. But they wouldn't know anything about the private because they're simply just private. So the public part is what external users depend on. And one example could be, if you look at, let's say you go to Java API, go to array list class. Everything you will see in the Java API documentation are the public method. Those are the things you know about. What about behind the scene? What about the private ones? You don't see them because they're private. Array list. API page. All right? And then, from the implementer points of view, the public stuff will depend on the private stuff. To implement the module, some public methods may be implemented using private attributes, right? So this should be quite easy to kind of imagine. I'm pretty sure you have done that, in all your Java courses. So for any public method, I might just use some private attributes. So here comes the information hiding principle. So public and also private, right? So here comes the information hiding principle. Whenever you are trying to maybe change your module, you don't really want to change this part here. Because whenever you change anything about the public, you're going to impact the customer or users using your module. Whenever you want to change anything, you better change the private part. That's really information hiding. Okay? So here is the principle. Changes to the module should be done to the private part without the user realizing it. That's principle number one. Right? Whenever you, as an implementer, if you actually want to modify something, it better be the private part you're modifying, which is only visible to you. Anything you're modifying the public part, it might impact like hundreds or millions of users of your class. Okay? That's principle number one. And principle number two, it's kind of similar. Okay? Principle number two. If a particular part of your module has to be changed often, then it better be declared as private. It should not be public. If a part of the module, let me use a different color so you can see that's two different principles. If a part of the module is changed often, it should be made private. Okay, so here I'm going to highlight the key phrases. Change often, then it should be private. All right? Because if the public part is actually changed very often, you're going to impact your user. You're going to annoy them because constant changes. So how do you apply information hiding to your project, for example? So you're going to review every class you're implementing and think about, for the public methods there, am I going to change them often? If I'm going to change them often, then they better be private. Okay, that's some principle you can apply. All right, information hiding. Questions? Okay. All right, information hiding, and then single choice principle. That one there, I wouldn't dive too much into it. It's just about whenever you can avoid code duplicates, you can use helper methods. Right? It's a single choice principle. Right? That one is easy. Okay. And then design patterns. You guys, how many of you haven't taken 3311 before this course? All of you have? You haven't? Okay, so that's okay. It's not really a prerequisite, but I would say for this course, we're going to need your knowledge from 2030 about polymorphism, dynamic binding, and we're going to learn about two design patterns. That's going to be directly relevant to the Antler 4 compiler project, right? One is called composite, the other one is called visitor, right? That's something I'll talk about in detail, so don't worry, I'll talk about it. Polymorphism and dynamic binding. So if you really want to do a little bit pre-study for that particular lecture, you may want to review polymorphism and dynamic binding from 2030. Okay, I do have some references on the lecture side for you. You can definitely try to do some study. Okay, finally, regression testing. Okay, this might be something you have done in the previous courses, but you didn't realize it's called regression testing, right? So for regression testing, let me talk about it as well, and then we can take a short break. Okay, regression testing. This one here, let me explain the idea about regression testing, right? I think the term comes from when you do readings, right? Let's say when you are reading some article, right? So let's say you got several lines over here. Regression refers to the fact that, let's say I'm reading here line by line. When I get to here, I kind of forget about what I have read previously. So I will go back to where I read before and go again. And once I get to here, I forgot about what I read already. So I go back to the beginning and then keep reading the same thing. That's really about the regression idea. And we said that in real life, doing regression when you are doing reading is bad. However, in software testing, regression is considered as good practice, meaning that you're going to keep running the same test cases over and over to make sure your software remains correct. Okay? So in 2030, I'm pretty sure you learned about JUnit test cases. So if you got a JUnit test class with maybe 10 test cases or 100 test cases, right? So let's say right now you got a green bar, everything passed. And then you go to your Java classes that's under test and make some changes. You cannot simply assume the new changes you made can just be correct. How can you make sure that's still correct? You got to rerun all the test cases to make sure you still get a green bar. That's really about regression. All right? Hopefully that makes sense, but let's just go over the workflow very quickly. And then that's something you will also need to apply in your project later, right? These are all good stuff. So what we got is, let's say you got your Java classes, right? That's your implementation, right? So this may be your implementation of the compiler. Implementation of your compiler. Because compiler is just a software project. And then you're going, as long as you're developing your compiler, you're going to run some JUnit test cases yourself to test the different methods of your compiler, right? So this part here is you are expected to write JUnit test cases while developing the compiler. Okay? So while you're developing the compiler is actually very important. So that means you shouldn't only start writing the test cases once the compiler is completely done. It's not the way to go. When you are doing it, right? Maybe for every method you're implementing for your compiler, you should really write some new test cases right away, right? So that's the recommended practice. So once you got Java implementation, once you got JUnit test cases, you're just going to use a JUnit framework. So the Antler 4 tutorial I'm going to show to you later, that one there uses Eclipse. But for you guys, you can feel free to use other IDE. I forgot if there's a requirement for the project, but I'll let you know a little bit later, okay? But anyway, let's say assume we use Eclipse, okay? Let's say we use Eclipse. Okay, the Eclipse comes with a JUnit framework, so you're just going to run the test cases and then to see if you get a green bar, right? If you get a green bar, so if you get a green bar, that means the software under test is correct. And if there's at least one assertion failure, then you'll get a red bar, in which case you have to go back to your Java classes and do some fix. So once you have fixed the errors, you can rerun the test cases and make sure you get a green bar ultimately. Right? So that's kind of the regression process. You got to keep running all the test cases, make sure you always get a green bar before you move on. Okay. Yeah, regression testing. Also good stuff, to make sure your projects always maintain to be correct. Right, just to name a few, so these are the nice principles I wish you guys will actually apply to your projects later, right? It's a very good way to actually maintain some good software engineering principles. Okay, why don't we take a very short break, and then we'll move on to stages of compiler. Okay, so before the break, we were up to regression testing. That was also one of the principles. Let's talk about some compiler. We're going to elaborate about the compiler component itself to see what it would look like. Okay, let's talk about it. Okay, you can think about, we used to talk about compiler that looks like this. Okay, let me just give you an idea, and then I'll talk about it. So this is a single compiler component that we spoke about just before the break, right? It's a single compiler. Imagine that we are now zooming in to that compiler component to see how it should look like. Okay, we'll try to zoom in about 1 or 2 times. Okay, zooming number 1. Okay, so this is how a compiler can look like. Okay, you don't need to worry about this one just yet. Okay, we're going to talk about it in detail. So you can think about this as a compiler, and then we got some input, we got some output. Of course, you got some CFG number 1, you got some CFG number 2 as well, like what we talked about, but they're omitted in this diagram here. Let's now talk about front end, back end, and also IR. Okay, so these are the idea that we're going to talk about. Okay, let's go over some slides, and then we do one exercise together. That's kind of interesting exercise to do together. Okay, so let's now talk about, go over some slides. Front end, which is right here. You can think about front end is basically your input program, your input. Okay, the front end is going to somehow encodes the knowledge about a source language. For example, if you got your source language being Java, so the front end should be just about encoding some knowledge about Java. What are the classes, and what are the attributes, and what are the methods? Symmetrically, if you get to the back end over here, the back end over here is about the knowledge about the output. Let's say if the output happens to be a relational database, then the output should, the back end should really encode the knowledge about tables, keys, queries, right? Front end and back end. Okay, so here we want to somehow, the front-end program is going to translate a source into some intermediate representation. Okay, intermediate representation is just some, you want to capture the ideas from the front end, from the semantic domain. Okay, I'll give you some example. And then you want to make sure whatever meaning it is in the source program, like a classes, objects, and also attributes and method, they are encoded properly into the intermediate representation. And then from the intermediate representation, you're going to convert that into the backend, to the final output. Okay, so that's the kind of idea. But we're just going to talk about what IR really is. That's something I will do. But you guys can go over the bullet points a bit, and then we're going to do this exercise together to get some concrete idea. Let's see that. Okay. So let's go back to this diagram here. You can think about the compiler itself has component number 1 and component number 2. Think about the front end is component number 1, which will transforms the input program to IR. And what's really IR? IR stands for intermediate representation. Intermediate representation. So let's say in the Java sense, intermediate representation can be just some classes you define with some attributes. Could be, right, when you do the implementation. And it is important to realize for the intermediate representation, it should be expressive enough to encode the knowledge about the input. Okay, I'll write it down here. It should be expressive enough, meaning that it should contain all the concept that's applicable to the input and output. Expressive enough to capture or encode the ideas of any valid input. So given some arbitrary Java program, can you capture all its idea in the intermediate representation? Okay, and then from that particular IR, you want to use the backend components and turn that into the relational database. Okay, so the backend will be component number 2. So component number 2 here is going to transform the IR into the output program. All right, let's do one exercise right away. All right, I'll let you guys to think maybe just for 1 or 2 minutes. 1 minute should be enough. Let's say here is a problem I want to give to you. Okay, somehow I want to implement compilers, a number of compilers. Let's say I want to have these 5 languages. I got Java, I got C, I got C#, I got C++, I got Python. I got 5 languages. I want to know, in order for me to implement some sort of compiler or compilers, how many intermediate representation do I need to encode the idea for example, if I want to go from Java to C, I might need 1 intermediate representation. If I want to go from C to C#, I might need another intermediate representation. If I want to go from C# to C++, I might just need another one. Right? So now the idea is, so now the question is, how many do I need if I want to have the exhaustive possible compilers to transform between all 5 languages? And before I take your insights, some hints you may want to consider would be, think about permutations. Okay. Yeah, I'll hear some thoughts from you guys first. I'll start with you.
Without giving the answer, you mean?
Maybe some thoughts. How about without giving the answer? How about that? Yeah.
Okay. So I'm thinking 1 IR between each one.
Mm-hmm.
The spaces in between are 4.
Mm-hmm.
And then we need 1 for each of those.
Okay, it sounds to me you're doing some permutation, right? Sounds like, for example, maybe what you meant, let me just make sure that's exactly what you meant. For example, in order for me to implement from Java to C, one IR. From Java to C#, another IR. From Java to C++, another IR. From Java to Python, another IR, and etc. Okay? It's really permutation. Okay? Let's now make this idea precise. Okay? Let's talk about it. How many IRs? Okay? One approach is to try to figure out the precise number of permutations. And I'm going to do the following. Okay? Let's say I got Java, and I got C, and I got C#, and then C++, Python. Oh, sorry, just let me double check. Okay. I just want to be consistent with the color I use, so that's why. Yeah. Give me just one moment. Yeah, there we go. Okay, let's say I got 5 different input languages. These are the inputs. And correspondingly, I might also have 5 possible outputs as well. And I'm just going to copy this column over here. Put it here. What your fellow student just said was 100% correct. I can say one compiler, I don't need to say go from Java to Java. Of course, it's going to be excluded. One compiler from Java to C. One compiler from Java to C#. One compiler from Java to C++. Another compiler from Java to Python. I got 4. All right? Let's just do one more. For example, what about a case for C#? So C# to Java, C# to C, C# to itself excluded, and also C# to C++, and also C# to Python. I also got 4. What will be the total number of permutation? Well, each one of them is going to need 4. I got 1, 2, 3, 4, 5. 5 times 4, 20. That's the naive way. Yeah.
So we're assuming that the compiler is one directional always, right?
We are, yes, typically. It's a good question here, yes. At least for this course and also for our project. We wouldn't say, oh, you want to implement compiler from input to output, also output to input. Not really. Yeah. Even though you could do that, but we don't go that far. Good question. Interesting. Okay. So here, so in total, we got 5 times 4 will be 20. Compilers. Okay, just to remind you, the 5 over here is about the number of languages we have, the number of input languages. And the 4 here is about each input, we only need to have the corresponding 4 because Java doesn't need to go to Java, right? That's a number of output, right? This one here is going to work, it's okay, but just very unnecessarily complicated. It's more like a software design issue here, okay? Now, how can I somehow minimize the number of intermediate representation? That's the question. Yeah?
Kind of going back to what someone else mentioned before.
Yeah.
Using the output as new input.
Using the output as new input.
So in the case of Java, for example.
Oh, I see what you mean. Okay, you're saying, okay, that one is interesting, could be another alternative. Yeah, you're saying that assuming that I got from Java to, let's say, C#. And then in order for me to implement from Java to maybe C++, I just need another one, maybe from C# to C++, just reusing some existing compiler. Yeah, that one is interesting. I haven't thought about it. It might work. Yep. But that one there, I need to think about whether it's going to be the minimum number of intermediate representation you will need. I got to think about it. Also, it's not general enough. Okay. Let me talk about the solution I'm thinking. Okay. Good. Another way is like this. That one there, you may want to think about the semantic domain for all the possible languages. I will somehow try to look at Java, C, C#, C++, and Python. Think about how to define the semantic domain. Is it possible to have some, to really analyze their commonality so we can share them to see, to group them into different groups? So what I meant was like this. I'm going to put some analysis of the semantic domain. Of course, this one is just a sketch. May not be 100% accurate, but you will see the idea. Okay? I can at least identify 3 semantic domains. Okay? I'm going to show to you. Okay? The first semantic domain is the basic procedural language. Basic. Such as, you may have if statements, you got loops, and also you got sequential composition. When I say sequential composition, I really mean you got one line followed by semicolon, another line followed by semicolon, etc. Right? Sequential composition. Okay, that's what I meant. So these are the basic procedural. And you got another semantic domain, which will be more about the advanced procedural. Let me use a different color. So this one will be the advanced procedural. One thing I can think of would be, let's say, pointer arithmetic. Right? In C, you can actually manipulate the pointer addresses. In which case, you cannot do that in Java or C#. Right? So that's the more advanced. That's not supported by every language. Pointer arithmetic. Okay, the final one. So you can think about this one here and this one together is about the procedural part. And also we got OO, object orientation, like classes, instances, polymorphism, etc. That one there is going to be another semantic domain, right? And that one there is about the OO. And the OO can be about the classes, and also about attributes, and also inheritance, etc. Right? So these are just different semantic domains. Let's think about once we got these semantic domain, somehow the languages we are talking about can be somehow put into different parts. Right? For example, let's say this one here. For example, this one here is supported by C++. C++ definitely can support pointer arithmetic. It can support basic procedure. Also, it can support object orientation. Right? So you will cover all the 3. And then you also got, for example, here, let's say here you got basic procedural and also OO. So let's say this part here. Okay, only this part. Okay, the gray one. This one here, for example, you got Java, you got C#, also you got Python. So this part here, basically, you support some basic procedure plus OO, but you just don't have the pointer arithmetic. Just don't have that, right? You don't have them in these languages. Right, so far we already covered 1, 2, 3, 4. We just got C. C does not support any OO, right? The final one, I'm going to put it here. So it's simply going to be right here. Okay, so this one here is going to be the C, right? So the exercise I'm doing here, in some way, you can think about in a general sense. When you are given so many input languages you want to support into compilers, you may want to sort of analyze what's the common features they actually share, and then try to draw diagrams like this so you can figure out what's the kind of IRs I can actually devise from there. All right, so given this idea here, I'm actually going to show you the final infrastructure for the compiler. Okay. So think about, I'm going to have one IR, for basic procedure. I'll call it IR1. I'm gonna get another one, IR2. Just for the advanced procedure. For now, just point to arithmetic. Just consider the idea. And also, I got another one, IR3. So here, I only got 3 of them. That means my compiler somehow is going to sit in the middle right here. This is my compiler. Compiler here, right? And then that one there contains 3 IRs, right? So that one there contains the IR1. Yep. And also we got IR2. And also we got IR3. Somehow they're just different. Again, this is about basic procedure, this is about advanced procedure, this one about OO, separate. All right? So that my compiler is able to handle the different combination of the IRs. And now, all I got to do is, I can now try to say, the input could be either the input here could be either of the 5. 1, 2, 3, 4, and also 5. It could be either Java, it could be C, could be C#, could be C++, or it can be Python. It can be any language. My compiler should be able to tell, okay, if you got Java, that means I'm going to somehow use the combination of IR1 and also IR3. From there, I should be able to figure out what the corresponding output should be. Depends on what you want to do. All right, so that's kind of the idea. All right, let me complete the picture. So here, it can also be either this, and also this. So that means I can also get either Java, or C, or C#, or C++, or Python. Okay. Let's say if I want to go from Java to C, let's say, let's try another one. Let's say I want to go for Java to, that's okay, Java to C. I'm going to cover IR1, and also this one could be challenging because Java itself only covers IR1 and also IR2. Sorry, beg your pardon. Java only covers IR1, which is here, and also IR3, which is over here. But for the output of C, it might require IR2, which does not necessarily exist in the input. So that kind of corresponds to what you asked earlier to me. Can we always transform from one thing to another? Not necessarily. Okay, I'm going to write it down. This is so important. Okay. So here, if you think about this diagram here, I'll put a star here. Java to C may not be feasible in general because Java can only be expressed using, so let's say Java here is going to correspond to IR1 and also IR3. IR1 and IR3. However, in order to generate C, that one there is going to require, in order to generate C, that's going to require, you're going to require this advanced stuff, which is not there. Okay. So for C here, it's going to require the IR2. Okay. Can only be used, IR1 and IR3. But IR2 is required by C. Is required by C. So it's a bit of crowded, but you kind of get the idea, right? So my point is, not necessarily it can always go from one language to another. It depends on what kind of concept you can encode internally. Okay. On the other hand, can you go from C++ into Java? Sounds quite feasible because C# C++ actually covers IR1, IR2, IR3. Java only requires IR1 and IR3. No problem, conceptually, right? Okay. So think about this kind of design architecture over here, right? So I think IRs here is actually a very important concept. Once you get to the project stage to really try to implement from input and output, these are also concerns you want to have. But most likely, the input to output should be feasible that we give to you. Right? We wouldn't give you something that's infeasible. There's no point. But it's a practical concern you want to have. Okay. All right, we're running out of time. Just give me 1 minute. I'll recap, and then we'll continue. Okay. So I think the most important exercise we did today is to talk about this idea about IR, intermediate representation. So please think about this particular naive solution where you're going to have one compiler for each input and output combination versus when you actually have the intermediate representation corresponding to the corresponding semantic domain for all the language features. And think about how you can translate between them. There would be some cases where it is not possible to go, for example, from Java into C because the output requires more knowledge that may not be available in the input. Okay, so that's the most important remark from today. Question?
Can Java and C use IR1? Or aren't they both
Can Java C? Oh, what do you mean? Can Java C both use IR1?
Yeah.
It depends on what your assumption is. If you're assuming that the C here is arbitrary C, then it might include pointers, which will be IR3. So that's not possible. On the other hand, if you're assuming that C here does not contain the pointer arithmetic, in that way, yes. In that way, you can go from Java with IR1 and IR3 and go to C. It depends on what your assumption really. Okay? Yeah. So my point is, if you really want to go from Java to C, you make it feasible, you have to restrict about the output you can generate. You definitely cannot go from Java and generate something that's a pointer arithmetic. You cannot do that. Yeah. All right, thank you so much. And then we're going to continue from Tuesday, and we'll definitely finish the introduction on Tuesday, right? And then we'll continue. All right.